We are in section 11.2 series. An infinite series is adding all the terms of an infinite sequence together. So we would add together all those terms. And notation for an infinite series is going to be the sum from n equals 1 to infinity of a sub n. And this is going to be a sub 1 plus a sub 2 plus a sub 3 plus and dot dot dot, going on forever. Then we also have a partial sum, and this is adding up only a portion of the series. So for example, if we had the sum from n equals 1 to 10 of a sub n, we would have a sub 1 plus a sub 2 plus, and we would go on, but we would stop at the last value that we would substitute in, which for this problem is 10. So a sub 10. And then right below that it says the nth partial sum, and the nth partial sum is given a series, the sum from n equals 1 to infinity of a sub n, which equals a1 plus a2 plus a3 and so on. It says let s of n denote the nth partial sum. So s of n is going to equal the sum from I equals 1 to n of a sub I. And so again, this is going to be adding up these terms, a sub 1 plus a sub 2 plus, and then continuing this on, but ending at a sub n. So adding together those nth terms. If the sequence, s of n, is convergent, and the limit as n approaches infinity of s of n equals s exists as a real number, then the series, the sum of a sub n, is called convergent. And we write that a sub 1 plus a sub 2 plus dot 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 plus a sub n plus dot dot dot, going on forever, is going to equal s, or that the sum from n equals 1 to infinity of a sub n is going to equal s. The number s is called the sum of the series. If the sequence s of n does not converge to a number s, then the series is called divergent. So if it doesn't converge, then it's considered divergent. The next definition that we have is called an infinite geometric series. And if you remember back from Algebra 2, a geometric series is one where you multiply by a value to go from term to term to term. And that value could be a decimal, a fraction, a whole number, positive, negative. And so we have a plus a times r plus a times r squared plus a times r cubed. And going on, we would have a times r to the n minus 1. And again, this keeps going. From this, we note that a is in every single term. So we can factor that out, and we have 1 plus r squared plus r cubed plus dot 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 plus r to the n minus 1 plus, and then going on forever, close parentheses. And so we can say this is going to equal the sum from n equals 1 to infinity of a times r to the n minus 1 power. And just a little note that a cannot equal 0. If a was 0, then we would have a 0 as our sum. And r is called the common ratio, which is the same thing that it was called back in Algebra 2. And that's that common value that we have that we multiply from term to term to term to get to the next. And so we have a couple things down here to note. First one is that if the absolute value of r is less than 1, then the geometric series is going to be convergent. So it converges. And the sum from n equals 1 to infinity of a r to the n minus 1 is equal to a over 1 minus r. And again, this is only for values of r between -1 and 1. And definitely a formula that we should know if this case arises. And the second case says if the absolute value of r is greater than 1, then the geometric series is divergent. And back in Algebra 2, you probably discussed this more in depth, but if r is less than 1, if it's in between -1 and 1, that means that you're multiplying by something that's causing each term to get smaller and smaller and smaller. Therefore, it's going to be convergent. versus if r is greater than 1 or greater or smaller than -1, then you're multiplying by something that's causing those values to get larger, either positive or negative, and then summing those up would obviously be something that's divergent. And so the next thing that we have is a finite geometric series, which is different than the infinite geometric series that we had up above. Finite means that it ends. And so we're going to say from I equals 1 to n of ar to the I minus 1 is equal to a times 1 minus r to the n over 1 minus r. And next below this we have a theorem. And the theorem states that if this series, the sum from n equals 1 to infinity of a sub n is convergent, then the limit as n approaches infinity of a sub n is going to equal 0. The converse is not always true. And then we have another test down here, and this is a test for divergence. I'm going to give that one 2 stars because this is a good one to keep in mind. This one says, if the limit as n approaches infinity of a sub n does not exist, or the limit as n approaches infinity of a sub n is not equal to 0, then we can say the sum from n equals 1 to infinity of a sub n is divergent. On the next page, we have a theorem that says if the sum of a sub n and the sum of b sub n are convergent series, then so are the series, and also considering c to be a constant. So this is the same thing as c times our sum from n equals 1 to infinity of a sub n. And likewise, 2, the sum of a sub n plus b sub n. If they are convergent series, then we can take the sum of each of these individually. And similarly, with instead of summing them together but taking the difference or subtracting, so the first example that we have says calculate the sum of the series from n equals 1 to infinity of a sub n whose partial sum is given by, so this is a partial sum, is given by s of n equals n squared minus 1 over 4n squared plus 1. And so this is a partial sum formula. It's not a sequence formula. So make a little note of that. This is a partial sums formula and not a sequence formula. And so we know that the sum from n equals 1 to infinity of a sub n is equal to the limit as n approaches infinity of that partial sum, as stated on the previous page. And so this is going to be equal to the limit as n approaches infinity of that formula that we have up above, which is going to be n squared minus 1 over 4n squared plus 1. And I'm going to multiply both the top and the bottom by that degree in the denominator, which is n squared, degree 2. So multiply both top and bottom by n squared, making sure all those terms it gets distributed to. So limit as n approaches infinity of, and we have n squared over n, which is just n squared over n squared, which is 1, minus 1 over n squared. And then denominator we have 4n squared over n squared, which is going to be 4 plus 1 over n squared. And so we know that taking the limit as n approaches infinity, 1 over n squared is going to go off to 0. And so we're going to be stuck with 1 minus 0 over 4 plus 0, which works out to being 1/4. So this is the sum of the series who has a partial sum given by this formula. And again, S of n is not a sequence formula. This is a partial sums formula. So the next example says find at least 10 partial sums of the series. Does it appear that the series is convergent or divergent? If it is convergent, find the sum. If it's divergent, explain why. So for the first thing here, we have the sum as n equals 1 to infinity of cosine of n. And so in order to do this, we need to find at least 10 partial sums. And in order to do that, I have to first figure out what the sequence is and figure out all those terms. So I'm going to need at least 10 values here. And so I have n and I have a sub n. And my a sub n is just cosine of n. So the different values of n that I would be substituting in. I'm going to start with 1 and it goes on to infinity. I'm going to be looking at those first 10 terms. And I need to have these in order to calculate my partial sums. And so using a calculator, I would have cosine of 1, which is 0.5403. Cosine of 2 is negative 0.4161. And then calculating the rest of these. So from the calculator, we get the remaining values. And if you notice, a sub n does not approach 0. And we should know that about cosine because it alternates between negative 1 and 1, those values. So a sub n does not approach 0 as n approaches infinity. And so in order to find our partial sums, make another table here and have n and s of n, and our values of n, the first partial sum, second partial sum, and so on. And so our first partial sum would just be that first value since there's nothing else to add with it. Second partial sum would be adding together these first two terms. And when we do that, we get 0.1242. Finding our third partial sum would be adding together these three terms, which is negative 0.8658. And continuing this on again with a calculator. And so from the calculator, we can calculate those remaining partial sums. And looking at the partial sums, it does not seem to be approaching a fixed value. So S of n does not approach a fixed value. And because a sub n is not approaching 0 as n goes off to infinity, and S of n does not approach a fixed value, we can say that therefore the sum from n equals 1 to infinity of cosine of n will diverge. The example on the next page says determine whether the geometric series is convergent or divergent. If it's convergent, then find its sum. First off, it tells us that it's a geometric series. So we had some formulas from before that we can talk about. The first example that we have is a list of numbers, and I am going from 4 to 3 to 9/4 to 27 over 16. And so we know that r, what we're multiplying by, would be equal to 3 over 4. And our first value, which is a sub 1, is equal to 4. And remember that if r, the absolute value of r, is less than 1, so meaning that if r is between negative 1 and 1, but not equal to those values, that means that it is going to be convergent. And then in order to find what it converges to, we had a formula on the previous page that was s equals a sub 1 over 1 minus r. And a sub 1 we know is 4, that's our first value. 1 minus r, and the common ratio that we have is 3/4. And so we get 4 over 1/4 or 16. So what this means is that this, as you go on from 4 plus 3 plus 9/4 plus 27 over 16, and it goes on forever, this actually converges because those values are getting smaller and smaller and smaller as we go, all those terms are. Part B says 2 plus 0.5 plus 0.125 plus 0.03125. And it might not be as obvious to see what R is in this case, and if you ever are unable to see that, you can take a value, one of those terms, and divide it by the previous term. So if I was looking at the first two terms, I would have 0.5 divided by 2, which equals to 0.25. And you can check that just by seeing if that's what you would be multiplying by to get from term to term to term. And it does tell us in this problem that it is a geometric series, so we do know that. And then our A1 value is equal to 2. And since the absolute value of R is less than 1, we would be able to say that this is going to be convergent. So the sum, again, is equal to A1 over 1 minus R, and A1 is equal to 2 over 1 minus 0.25. And so this is going to be equal to 2 over 0.75, which works out to being 8 over 3. Part C is written with sigma notation instead of as a list of numbers. And so we have the sum from n equals 1 to infinity of 10 to the n over negative 9 to the n minus 1. And so I'm going to rewrite this. It's a little difficult to see what R is in this problem. You can write out the list of numbers just like how it looked in A and B and see if you can figure out what R, the common ratio, is by that. But I'm going to try a different method and just trying to rewrite this. So I have n equals 1 to infinity, and this is 10 to the nth over, and we can separate this and say negative 9 to the nth and negative 9 to the negative first. So negative 9 to the nth and negative 9 to the negative first. Remember that when you multiply things that have the same base, you would add together those exponents, and you would get that n minus 1. So the negative 9 to the negative first, since it's in the denominator, means it's going to move to the numerator, and that would be a negative 9. And I'm going to put that out in front of my sum, just because that is a constant value, and that was one of those rules that we had from n equals 1 to infinity of, and since we have 10 to the nth and negative 9 to the nth, they're both raised to the same power. So I can rewrite this as negative 10 over 9 to the nth power. And so looking at our formula, which was A times R to the n minus 1, or n, this would be our R value in here. And so our R, our common ratio, would be equal to negative 10 over 9. And again, if you wanted to, you can write out term by term by term just to see that, and it would look similar to what A and B is. And so because R, the absolute value of R, is greater than 1 this time, this means that this is going to be divergent, and so this diverges. So right below this, we have some special cases. The first one that we're going to talk about is a harmonic series. And so with this, we have the sum from n equals 1 to infinity of 1 over n is equal to 1 plus 1/2 plus 1/4 plus, and this goes on forever, and this is going to be divergent. And proof is written out right below for us. So it says the sum from n equals 1 to 1 over n and to infinity is equal to, and it's written out there for quite a few terms. And then from there I grouped them. And so I grouped together the first one, the second one, the next two, the next four, and rewrote it a little bit. And then I said that that is greater than or equal to, and then rewrote it again, and then rewrote and said that because it's greater than, I just made the smallest one that was in that group to be the same for all of those other fractions. And then adding it together, if you notice, the 1/8 plus 1/8 plus 1/8 plus 1/8 would be 1/2 also. And so you would add these all together and it would keep going for forever. and that's going to equal infinity. So it's going to be divergent. So we have an example right below, and this says determine whether the series is convergent or divergent, and if it's convergent, find its sum. And so we have the sum from k equals 1 to infinity of k times k plus 2 over k plus 3 quantity squared. And so in order to figure out if this is going to be, this series is going to be convergent or divergent, now look at the limit. And the limit as k approaches infinity of, and I'm also going to rewrite this a little different. I'm going to distribute in that k in the numerator, so k squared plus 2k, and then multiply out k plus 3 quantity squared, and we get k squared plus 6k plus 9. And then multiplying both the top and the bottom by 1 over k squared, which is that degree in the denominator, like we saw in Calculus 1. This is now going to become the limit as k approaches infinity of, and then making sure to distribute this to everything in both the numerator and the denominator. And so we end up with 1 plus 2 over k, and the denominator is going to be 1 plus 6 over k plus 9 over k squared. And again, as you take the limit of 1 over something infinitely large, these are all going to go to 0. And so this is going to equal 1 plus 0 over 1 plus 0 plus 0, which is equal to 1. And this value does not equal 0. And so if we look back at the test for divergence, and the test for divergence, which is at the bottom of page 5, says if the limit of as n approaches infinity of a sub n does not exist, or the limit as n approaches infinity of a sub n is not equal to 0, then we can say that this series, the sum from n equals 1 to infinity of a sub n, is divergent. So since this is the case of where the limit does not equal 0, and so since this limit was equal to 1, which is not 0, we can say that this diverges. And this is by, you need to make sure that you state why. So this is by the test for divergence. Part B says the sum from n equals 1 to infinity of 1 plus 3n over 2 to the nth. And this one reminds me of a geometric series, just because it's a number raised to an exponent that is the same as the index for the sum. And so again, we're going to go ahead and try the limit as n approaches infinity of 1 plus 3 to the nth over 2 to the nth. And this is identical to the limit as n approaches infinity of 1 over 2 to the n plus 3 to the n over 2 to the n. And then we have the limit as n approaches infinity, and I can look at each of these individually. So I'm going to rewrite this as 1/2 to the nth power plus the limit as n approaches infinity of 3 over 2 to the nth power. And so this first one here, the first limit that we have, actually is geometric. And our R value is equal to 1/2. And since the absolute value of R is less than 1, we would say this converges. And we can figure out that sum by using that little formula that we used in the previous examples up above, with sum is equal to A1 over 1 minus R. But we also need to look at our second limit, which for this one, it is also geometric. And this time R is equal to 3 over 2. However, our R value this time, the absolute value of R, is greater than 1, which means that this one is going to be divergent. And even if that first limit converged to some value, adding on something that diverges to infinity would equal infinity also. And so therefore this diverges. And so we can say this diverges because, and we have a couple different options here. One is just because it's of the geometric series test. And so because this is a geometric series and we know that r, the absolute value of r, was greater than 1, we can say that this doesn't converge. And we can say diverges because geometric series test and the absolute value of r is greater than 1. So we can also say that this diverges because of the test for divergence, because the limit as n approaches infinity of 1/2 to the n plus the limit as n approaches infinity of 3/2 to the n is not going to be equal to 0, which it needs to be. And if it's not equal to 0, then we can say that it diverges. The next page has 2 more examples with the same directions. So part C says the sum from n equals 1 to infinity of 3/5 to the n plus 2/n. And again, I'm going to go ahead and look at these each separately since they are really different. The one looks more geometric than the other. And so I'm going to go ahead and say this is equal to the sum from n equals 1 to infinity of 3/5 to the n plus the sum from n equals 1 to infinity of 2/n. And those constant values can pull out in front. So I'm going to go ahead and put the 3 in front. And I have 1/5 to the n plus 2 times the sum from n equals 1 to infinity of 1/n. And if you caught it, this is harmonic. And because this is our harmonic series, we can say that this is going to be divergent. So our series will diverge since we have a harmonic series in this problem. We have one more on here which says the sum from n equals 1 to infinity of e to the n over n squared. And this one looks a lot different than anything that we've seen so far. So I'm going to go ahead and rewrite this as the limit as n approaches infinity of e to the n over n squared. And I am stuck because right now evaluating this, it would be infinity over infinity. And so this is indeterminate. And so what we did before was to divide all the terms by the degree in the denominator. However, it doesn't work for this one since I do have an exponential and a polynomial. And so I'm going to go ahead and use L'Hopital's rule. And L'Hopital's rule again was taking the derivative of the numerator by itself, which is just going to be e to the n, over, and taking the derivative of the denominator also just by itself, which is going to be 2 to the n. Evaluating this still, as n approaches infinity, we still get infinity over infinity, which still is indeterminate. So again, we use L'Hopital's rule for a second time, and we have the limit as n approaches infinity of e to the n all over 2. And this is going to equal, as n approaches infinity, we would have something infinitely large over 2, or just infinity, which clearly is not going to equal 0. And so this is going to be divergent also. And I'll say by the test for divergent. So by the test for divergence. The next thing that we have is a telescoping series, which is another one of these special cases that we'll see. And this is using partial fractions. This would be the same thing as n equals 1 to infinity of negative 1 over n times n plus 1. And rewriting this, if you were to substitute in 1, which is the first value of n, we get 1/2 minus 1 plus, and then 1/3 minus 1/2 plus, and then the next term we have 1/4 minus 1/3. Substituting in 4, we have 1/5 minus 1/4 plus, and this goes on forever. And we end up with 1/n plus 1 minus 1/n. And I'll put plus ... down there. And so if you notice on this, some of the terms are actually going to be canceling out. So you have a 1/2 and a negative 1/2. You have a negative 1/3 and a positive 1/3. You have a negative 1/4 and a positive 1/4. And this is going to continue with them canceling out. And the terms that are going to be left over with are going to be 1/n plus 1 minus 1, which is in here in the beginning. And again, this 1/n would have canceled with the other term that was in front of it. And so this would be our telescoping series. And so we have an example down below that we're going to go ahead and circle, and we'll look at this one together in class. The example on the next page says to express the number 0.46 repeating, which is equal to 0.46, 46, 46, and so on, as a ratio of integers. And so we have 0.46 repeating. And to think about this as a ratio, I'm going to go ahead and think of this as 46/100 to get those first numbers, the 46, plus 46/10,000, which is equal to 0.0046, so that gives me the second 46, plus 46/1,000,000, plus, and this would keep going on forever. And so we can think of this as being 46 over, this would just be 100 to the first power, plus 46/100 to the second power, plus 46/100 to the third power, and so forth. And so rewriting this with a sigma notation, we would have the sum from n equals 1 to infinity of 46/100n. And to rethink about this, we can say this would be equal to 46, the sum from n equals 1 to infinity of 1/100 raised to the nth power. And r, which is our common ratio here, would be 1/100. And so we would say that this converges. And in order to find that sum that we would have, since it does say to express the number as a ratio of integers, to find that, we know that a1, our first term, if you were to substitute in 1 for our value, we would have 46/100. And so our sum is going to be a1 over 1 minus r, which is 46/100, all over 1 minus 1 over 100, which equals 46/100 all over 99/100, or 46/99. So in order to rewrite this as a ratio of integers, we broke it apart and thought of it as a sum of adding together all these pieces, and then figured out that to find that sum of adding together all those pieces by using s equals a1 over 1 minus r, since this is a geometric series, and r is equal to 1/100, and our first value a1 is equal to 46/100, we were able to say the sum is equal to 46/99, which is a ratio of integers. The next example right below, I'm going to go ahead and circle, and we will work on that one together in class.